Okay, so I do have graded homework problems that I will put up here, and you can grab them after class. They're due on Friday, and I posted an electronic copy of them as well. They deal with orbital pictures, polar, non-polar, intermolecular forces, and then writing resonance structures and hybrids and ranking. So you can pick one of these up after class. Okay, so for the naming sections here in the Top Hat textbook, I don't really have, outside of alkanes, I don't really have videos for these. So what I'm going to ask you to do is kind of read through as best you can the book, material for each class, but then I'll spend time lecturing and going over those, because I don't have videos to go with those, and it's unlikely I'm going to take the time to do them when I can just do them in class. All right, so questions?
Can we go over what common names are, what they replace, and what the ISO means?
Okay. Okay, so first of all, this book does something I wish it would not have done. And what I wish it would not have done is I wish it would not have mixed in or made a distinction between common names of alkyl groups and IUPAC names of alkyl groups. So let me show you what I mean by this. There's some problems there. So what they did was something that I thought most organic books has gotten rid of, but they didn't. And that is that the naming for the branched alkyl groups. So from your book, this is the listing of the branched groups. In bold is what is the official IUPAC name of them. Now, they may have called these common names, but I'll explain. IUPAC has accepted those common names as being IUPAC names. So all of the ones in parentheses are not accepted anymore. And if you go to the website, if you go to Canvas for today, there is a alkyl group names that you can click on, and it has a handwritten sheet by me that has all of the alkyl group names that you need to know. So these are all alkyl groups that have an accepted IUPAC name. That's methyl ethyl, propyl, isopropyl, butyl, isobutyl, secbutyl, tertibutyl, and then into pentyls. Those names have all been accepted by IUPAC. Now, there was a time a few years ago when there were common names and there were IUPAC names, and IUPAC had their own names, which are the ones in parentheses. But the one below that says IUPAC common names and groups, this has the actual pages from what's called the Blue Book of IUPAC that tells you how to name organic compounds, and they use a different terminology because they're IUPAC. So the following names may be used for unsubstituted radicals, which means alkyl groups. And so they've accepted isopropyl, isobutyl, secbutyl, tertibutyl, isopentyl, neopentyl, tertipentyl, and isohexyl as official IUPAC names. So the ones in parentheses in your book are gone, except they're not gone. If I could scribble through them, I would, but I don't think they let me do that. So we are going to use these these names in yellow and the names that were in that sheet that I hand wrote. Okay. So for a while, in the common name system, basically, you discover it, you name it. And then if everybody accepts that name, it became the name. So that's where the isopropyl and the terpeneol and all of that came from. But IUPAC says that there is one and only one name that anybody will write for an alkane or for any group. Their rules are set up specifically so that no one will write a different name if they're following their rules. And if their rules give more than one name, then they're bad rules. They need to be replaced. And they spend a lot of time on rules. So if I use the parentheses names, like instead of isopropyl, I use 1-methyl-ethyl, then I could come up with 2 correct names, which violates IUPAC rules. So you're going to be required to just know the isopropyl, terbutyl, sec-butyl, etc. Okay. So the ones that are in the book in parentheses you can ignore. And I can explain how they came about, those names, because we may have to do that in the future. Right. So that's the first thing is we're going to use the isopropyl, terbutyl, etc. Now, what is an isopropyl group? What is an isobutyl group? Just because they're common names and somebody came up with them doesn't mean there's a system to it. Because there kind of is. And the system is, number one, in the book they do this. They go, parent. It's like, what's that? Well, imagine that I have a long chain and I have that group attached to it. My first rule in coming up with the IUPAC name of this alkane is to find the longest continuous carbon chain. There's some tiebreakers along the way. But once I find the longest continuous carbon chain, that is called my parent chain. And everything off of the parent chain is a substituent or an unsubstituted radical, according to IUPAC. But I like substituent better. So we name the parent group, we circle the parent group, we do whatever is necessary to identify the parent group. Everything that's left over is the substituent. So when they write this, when they write parent, they're meaning the longest chain in the molecule. They could also mean a cycloalkane ring, like a cyclohexane. So I erase it. And so what I'm looking at is I'm looking at this being the attachment point to the longest chain. What I suggest when you look at a group like this, write your carbons in at the intersections of lines and at the end of lines, and add enough hydrogens to get you 4 and only 4 bonds. And that may help you, well, we're going to have to use the M word here, memorize those groups, their structures, and their names. Okay. So the straight-chained, non-branched alkyl groups are easy. Because if you want a 3-carbon chain, just have a 3-carbon chain like that, no branches, attached to the parent group. That's a propyl group. And for all of these commonly accepted IUPAC names, the total number of carbons is their parent name. So anything with 4 carbons is going to be butyl. What kind of butyl? Depends. Anything with 3 carbons is a propyl. So a straight-chained propyl group is a propyl group. There used to be an N in front of it for normal. They have jettisoned the N. I wrote a paper probably 8 or 9 years ago, and we were doing N-butyl lithium, and the referee's like, you can't use N anymore. It's just butyl lithium, because it's like saying the, and I'm like, whatever. I'll erase the N's, just accept it so we can move forward. So N is not in vogue anymore. Who knows? Maybe it'll come back, but it's gone for now. So you've propyl, butyl, pentyl, decyl. That just means it's a straight-chained, unbranched alkyl group. It's the branched ones that have issues, right? They have special names. So this is called isopropyl. 3-carbon chain propyl. An iso group. Again, these are common names. Somebody came up with this, but they did put a system to it. An iso group has a CH3 attached to a CH attached to a CH3. So that is an iso group. If it's only 3 carbons long, it is isopropyl. If that iso group is now attached to a CH2 that's attached to something else, that is now a butyl group with an iso group. So that would be called isobutyl. Now the critical part is an iso group is a CH3, CH, CH3. Got to have those 3 atoms connected that way. So that's what an iso group is. Even for the common names, except one, there is a system that they applied to come up with those names. So the first thing is, if it's not straight chained, then look for an iso group. If it's there, it's iso, whatever the total number of carbons is. If the iso group's not there, it's something else. And the only other 2 things it could be up to 5 carbons is it could be a sec or a tertiary. If something doesn't make sense with all of this stuff, you got to yell.
Would you say there's no iso group?
Well, then we're left over with sec and tertiary. So for instance, butyls. Straight chain butyl, butyl. Isobutyl, isobutyl. What happens if I take my butyl group? Let's say I just take my 4 carbons here. If I make the attachment point at the end, it's N-butyl. If I make my attachment point in the middle, so that it looks like this, that is going to be sec-butyl. How did that name come about? First of all, it's butyl because it's 4 carbons. Secondly, forget about what it's attached to. Okay? Forget it. Cover that up. How many carbons are attached to that carbon? Not including what it's attached to. There's 2 carbons attached to that carbon. And so what kind of carbon is that? It's a secondary carbon. And so this is a sec-butyl group. This is the only arrangement for a butyl group where the attachment point is a secondary carbon. And because it's unique, it has a unique name and a unique structure, it gets, sec-butyl got upgraded to be an IUPAC name. So there is a system to this. Drawing it out. Like, what do you want to?
Draw out the isobutyl as like whatever it was, the CH3, attach the CH, attach the CH3. Is there like a different format?
No, once we get to sex and sec butyls and tersh butyls, it's just that group. So this is not iso, because iso would have to be CH3, CH, CH3, and it is not. So this is a sec butyl group. So if you want, it's attached to a long chain.
So it would be a CH3, CH, CH2?
CH3.
No, not for it to be iso, for it to be sec.
For it to be, oh no, sec is sec. Sec could be, well, this is a sec butyl group. So what sec means is it just means this is the butyl group whose attachment point is a secondary carbon. That's what it means. There's no sec group. There's an iso group, but there's no sec butyl. And there's no tersh group. It just means the way you would read this is the only arrangement of 4 carbons as an alkyl group where the attachment point is a secondary carbon. And that's why we call it sec butyl.
Is this discussion only dealing with the alkyl groups, not?
Well, I mean, you can label carbons as primary, secondary, tertiary, or quaternary. And you can do that, but right now where it's most important is this is where these names come from. So if you try and create some other butyl group as an alkyl group, you will not be able to come up with one other than this where there's a secondary carbon attached. And you might come over here and say, well, what's that? Well, that's a primary carbon, but it's got an iso group, so it's isobutyl. And actually, all the iso groups beyond isopropyl all have a primary carbon attached. That doesn't lead to any names. Only the fact that it has an iso group leads to a name. Make sense? Yes? No?
Can you go over like how you know which carbons are primary and which ones are secondary?
So if you had an alkane, or well, we could do it this way. What kind of carbon is the CH3? How many other carbons are attached to it? 1, so this is primary. How about this CH3? It's primary. How about this CH2? It's secondary. You only count the carbons though. So for instance, if I go over to the drugstore and I buy isopropyl alcohol, rubbing alcohol, that's what it would be called, as isopropyl alcohol. Why? Because there's an isopropyl group attached to an OH, which we'll find out in a couple of days is an alcohol functional group. So this is isopropanol. What kind of carbon is that? Primary, secondary, tertiary, quaternary? It's secondary because oxygen doesn't count. The only thing that counts? Carbons. Carbon's the only thing that counts. And I think someone asked a question on Piazza that way, and I think I went through and I color-coded all of the atoms. So if you haven't seen that, that's also, I showed how you would get that. With alkanes, it's just a CH is tersh, a C with no hydrogens is quat, a CH2 is secondary, and a CH3 is primary. And a CH3 will always be primary, unless it's just a CH3 group, at which point it's methyl. But if it's attached to one other carbon, it's primary. So that's where these names come from. So then you might, let's see. What's that? The whole group. What's the whole group? This is a tertiary butyl group. How many carbons does it have? 4 butyl. What's the attachment point? A tertiary carbon. So that's a tertiary butyl group.
Would you call it like neo? Because like in the video.
So neos don't happen until 5 carbon groups. So in the 5 carbon groups, we've got a 5 carbon straight chain, unbranched would be pentyl. A pentyl with an iso group is isopentyl. Someone, whoever discovered this is the story that I tell. I have no idea whether it's true or not, but it makes sense to me. There is a pentyl group that I suspect, or it helps me remember this, that when somebody came up with that in the common name era, where you could just you discover it, you name it, they said, wow, that's a new pentyl. So they decided to call it neopentyl. And they couldn't just they didn't name it after their pet or anything like that. I mean, they could have. So there are rules. But that is a new pentyl. So that's called neopentyl. Is there a tertiary pentyl? Okay, I need a tertiary carbon. So I need a carbon attached to 3 other carbons, and I need a 5 carbon total. So that means attached to that tertiary carbon are 2 CH3s. And then to get to 5 carbons, I need a CH2CH3. So that is a tertiary pentyl. That is the only arrangement of 5 carbons that I can draw where a tertiary carbon is the attachment point.
So basically what you're saying is if you see that as tertiary pentyl, like there's no other...
There's no other tertiary pentyls. There's no other pentyl that has a tertiary attachment point. So that's why, remember, IUPAC rules are each name has to be unique. Okay. So, let me ask, I'm missing one, or am I? Which one haven't I drawn? I got a tertiary, don't have a sect pentyl. Now I could ask you, I could say, why don't you write an arrangement of 5 carbon atoms where the attachment point is secondary? There's one. There's one. There's one. So in the pentyl in the pentyl groups, the naming breaks down. Because if I say draw the structure of a sec pentyl group, you would only be able to draw one. And there are multiple arrangements here. So there is no sec butyl pentyl. There is no sec pentyl.
For the sec butyl one, couldn't it also be attached to the carbon to the right of it? And be secondary?
You want a sec butyl? Sure. Same thing. They're the same group. So, take that group and do this. Flip it around. What's critical is the CH has a methyl and an ethyl. This CH has a methyl and an ethyl. Same group. In general, what we're going to find is if you name two molecules with the same name, they are the same structure. So that's why it's important to go over naming first. Because if we need to know if two molecules are the same, we name them. If they have the same name, same molecule. Somebody just named it. They came up with this structure, which is unique.
So that's the only one.
That's the only neopentyl. There might be a neohexyl if you put another CH2 on the first CH2, but we're not going that far. So it's just somebody came up with that structure. It's a unique structure. They said, hey, it's new. We'll call it neo. And now IUPAC has accepted it as an IUPAC name.
So on the third slide, what would you name those?
So on these ones, what would I name them? Do you really want to go there? These are what are called complex substituents. Without IUPAC common names. So these are groups that don't have a name that's been accepted by IUPAC. So then, in order to name these, you need to follow the IUPAC naming for complex substituents. A complex substituent is one that doesn't have a name. A simple name, like neopentyl, isopentyl, etc. So the rules for this are at the bottom of that page where I wrote out all of those. But here's what we do. You ask the question, I just answer. So what we do is we find the attachment point. Now, when you're doing alkanes, what's the first thing you do to name an alkane? You find the longest continuous carbon chain, then you number from the end closest to the first substituent. This is reverse. The attachment point is automatically number 1. In an alkyl group, that's number 1. Now I find the longest carbon chain. So if I go to the left, it's 2. If I go to the right, it's 4. Now this is an alkyl group. So that means the 4-carbon chain makes this group a butyl group. And what's attached to the butyl group? At carbon 1, there is a methyl. So this would be a 1-methyl butyl group under the IUPAC rules for naming complex substituents.
For naming complex substituents, does it not follow the alphabetical order?
It would. Well, you mean when I get to putting it in the naming scheme?
Yeah.
I'll get to that in a minute. Because we got to do one thing with this before we can get to that. what would this one be called? I got to start numbering at the attachment point. What's the longest chain? 3. So does it matter if I go left or right? No. Go right. So this is a 1-ethyl propyl group. Oops. And then here, this is carbon number 1. Automatically. So do I go left or right? Left. Number 1, 2, and 3. Does it matter if the 3 carbon was down? No, same thing. What's this one called? 1, 2. Propyl. Now, every one of those complex names goes into parentheses. And it goes in parentheses because that's the group. So the parentheses say 1-methylbutyl is a group. 1-ethylpropyl is a group. 1,2-dimethylpropyl is a group. That's the group. So where you saw these parentheses before was in the book, because they were using this system to name tertibutyl and isopropyl, which now IUPAC has said we don't use those anymore for those molecules because I've accepted their common name. So isopropyl was 1-methylethyl. Tertibutyl was 1,2-dimethyl ethyl. Been doing this a long time. I can see it in my head. We had a book that only used those stupid bracket names, and it drove me up the wall because I couldn't say, well, that's a tertibutyl group. Oh no, that's a 1,1-dimethyl ethyl group. Because they decided to use that system. But they quickly changed out of it.
So the tertibutyl stuff does not go in parentheses?
No.
Okay.
The tertibutyl is its own name.
Okay.
And that's what we like. We like tertibutyl, we like isopropyl. These guys don't have names. These alkyl groups do not have names. So in order to name them, we have to give them a complex name which goes in parentheses.
Can you go over how to number those cards again?
So you have to start at the attachment point as number 1. Then I'm going to go left, right, or up. I'm going to go off in all 3 directions, and I'm going to find the longest chain. So in this case, my longest chain is 4. In the second one, it doesn't matter whether I go left or right because it's a 3-carbon chain is my longest chain. And over here, it's got to be a 3-carbon chain because that's the longest chain. So you start automatically at the attachment point and then go to find the longest chain.
And also, what makes the 1-methyl and then the 1-methyl? Because I both CH.
So this is a methyl, this is a methyl, so that's a 1,2-dimethyl. Up here, these are ethyl groups. It's a CH2CH3 that's attached. Well, sorry. The way I numbered it, this is the ethyl group over here. So that's an ethyl group attached to a propyl group at carbon 1. And over here, this is a methyl group attached to a butyl group at carbon 1.
Do you go over how you would name it if you attach a cyclohexane?
So the reason we put these in brackets is twofold. Number 1, we're going to have names of other groups that are attached to the longest chain. So I don't want those getting confused with this group, so I put it in parentheses because that's the group. So I want to set it apart. So if I had a cyclohexane group with, let's say, a methyl group here and a I'm out of space. And the 1-ethylpropyl group there, if I'm naming this cyclohexane, which I probably should have put this in a long chain, but if I'm naming the cyclohexane group, I've got to find the numbering scheme that gives me the lowest sum, which is either 1, 2, or 1, 2. So who am I going to start at? Methyl or 1-ethylpropyl. So that's why I would name this. I would say this is methyl, and in parentheses, this is 1-ethylpropyl. So alphabetization is going to be critical in this case. So I'm going to start numbering at the first alphabetized substituent. What? Well, that's what I was going to say. Well, what's our rules for this? Now, remember how di, tri, tetra? Do you alphabetize on those? No. Well, there's one time you do. The rule for parentheses is that if there's a name in parentheses, the first letter, regardless of what it is what you alphabetize on. So, for instance, that E in ethylpropyl is what we're alphabetizing on, because it's the first letter in parentheses. And that rule holds even if there was a di or a tri. So if you had a 1,1-dimethyl hexyl, that would actually be alphabetized on the D, because the parentheses rule is you alphabetize on the first letter. So in this morning's class, I was kind of like, well, you know, we don't number on di or tri most of the time. And then nobody said, well, when don't we? Because we didn't actually go over this stuff. They didn't ask about this. But this is when di and tri are actually alphabetized, is if it's in parentheses. So as soon as it's in parentheses, whatever the first letter is, that's what you're alphabetizing.
When is it put in parentheses?
It's put in parentheses when the alkyl group cannot be named by methyl, ethyl, propyl, all those ones that you have to learn. So if it's a group other than that, you have no choice. You've got to put it in parentheses. And this is the scheme in which you would come up with that name.
Is this something the book went over, or is this just like a side concept?
No, I think it's in the book. I don't know that they. Well, I'm sure they talked about the parentheses because they're using them. And if not, I think you'll see stuff I added to this chapter on that.
So then the name for that is parentheses, methyl.
1,1-ethylpropyl. Well, the 1-ethylpropyl's in the parentheses. Where is that 1-ethylpropyl attached to? Attached to carbon 1, so there's a 1 outside the parentheses. And then 2-methyl cyclohexane. So there's two reasons you put the name in parentheses. Number one, so that the ethyls and propyls don't get mixed up with everything else. Number two, because there's a number that has to come outside the parentheses to tell you where that group is attached.
So how did you decide that it was like the one ethyl and it's not one ethyl?
Well, because remember what is this group? This group is this one, which is a propyl group with a 1-ethyl group attached to it. So its name is 1-ethyl propyl, and the propyl comes last because that's essentially the parent name of the alkyl group.
But how did you know that it was attached to the one carbon and that methyl wasn't the one carbon?
Oh, I just alphabet. So I have two numbering schemes. That's my first rule. So whether I numbered it 1, 2, or 1, 2, I get the same sum. So now to break that tie, we have to start at the first alphabetized substituent. Okay. So that's the tiebreaker on cycloalkanes. And I believe someone asked me about that in Piazza, so I believe there's a longer answer to that there as well.
What is the one inside the parentheses?
It comes from the fact that this is a propyl group right here with an ethyl group attached to carbon 1. Because you could imagine I might have another propyl group. Just imagine, this can't happen, but maybe I have a propyl group with an ethyl attached to carbon 2.
Can you do an example of one of the, like, bicyclics or whatever that was?
The Bicyclics?
Yes,
Sure.
like the ones with the bridge heads.
Is everybody sort of okay with? We're going to be going, I mean, all the naming stuff we'll be going back over. So on Wednesday, if something doesn't, we can go back over. Because if you don't know your alkyl groups, you're not going to know the rest of the naming. But bicyclics. So how do you name bicyclics? Substituents are an issue. So, and after I do it here, there's also one on, again, Piazza. It's hard to keep track of Piazza because it's like a whole separate lecture. After I answer like 5 or 6 of these a day, and that's okay. That's what I get paid to do. But it feels like a whole other lecture. So if you just search through those, you'll see some of the answers to these. They're short term. Not short, but they're short term. Okay, this is a bicyclic compound. The bicyclic compound basically means that we have carbons where we have 2 rings that are fused together by 2 attachment points. At least 2 attachment points. So this is a bicyclo compound. A bicyclo compound has its own naming scheme. So it is a bicyclo in brackets, 3 numbers, number dot number dot number, bracket, name, A&E. This name is the total number of carbons in the bicyclic structure. So in this molecule, I would have 1, 2, 3, 4, 5, 6, 7. So this would be a bicycloheptane. Okay, I'm just showing you the ring system. There's no substituents on this yet. Okay, so this is a bicycloheptane. What are the 3 numbers in the brackets? Well, first of all, there are 2 carbons that are basically going to be at least tertiary. They could be quaternary. So they are what are called the bridge. These are called the bridge heads. These are the bridgehead carbons. That and that. So those are the bridgehead carbons. And if you have 2 bridgehead carbons, I can kind of think about this as, let's say I put a shaft there, and what I have are like 3 what I call propeller blades. So I have a propeller blade here in yellow. Here in green. And here in blue. So I basically have 3 propellers. If you looked straight down those 2 bridgehead carbons, there's 3 propellers. And so the size of those propellers and carbons is what goes into the parentheses. So if I look over here, I've got a propeller that has 2 carbons. Over here I've got a propeller that has 2 carbons. And up here I have a propeller that has 1. So what I would call this, and we go in decreasing numerical order. So this would be a bicyclo 2,2,1 heptane. So that means that it has, of the 3 sides, it's got 2 carbons, another 2 carbons, and 1 carbon that make up basically the 3 propellers of the bicyclic compound.
So for that example, if it only have propellers in those locations, or can it move around?
I can rotate that thing around. This isn't going to look very good, but I could do this. I could say, I could write it like that. But still, here's my 2 bridgeheads. There's still 2 there, there's still 2 there, and there's still 1 there. So that's how you name the system. Now, okay, so this is total number of carbons. These are the number of carbons in the propeller system. One of the things that you can check against is that this sum will always be 2 less than your total because you don't count the bridgeheads in your brackets. So if there's 7 carbons total, then the bracket should add up to 5. So that's a 2,2,1.
So if you have a branched bicyclic, I was a little confused, like I couldn't quite read it, like in how to number that, like that was a little confused. I think I got it, but I just kind of want to see it exactly that.
Okay, I'm going to add an extra carbon to one of the 2 sides. Here's the rules. The rules are, well, I need to put a substituent in place. Methyl. So, bicyclo bracket, 1, 2, 3. 3.2.1 bracket, that's what? 6 octane, because I have to add 2 on for the bridgeheads. So here's my bridgeheads. This is a bicyclo 321 octane. This is a methyl bicyclo 321 octane. The question is, what number goes with the methyl? And here's the goal. The goal is to get the methyl group the lowest substituent number. But again, I need rules so that everybody gives it the same number. Okay? So the bicyclo 321 octane is the parent name. I need to follow these rules. Rule number 1 is that I must start at a bridgehead. Okay, well I got 2 of those. And I can go left or right off of each one of those, so that's 4 possibilities, so I need another rule. Remember, my goal is to get the methyl the lowest number. Rule number 2 is start at the bridgehead, then go through the longest propeller, then the, let's say, medium propeller, medium-sized propeller, then the shortest propeller. Now, I am only allowed to pick up my, when I go 1, 2, 3, 4, 5, that has to be in a continuous motion until I get to the third propeller. Okay. So, how am I going to get the methyl group, the lowest number, following those rules? I'm going to start with B. I heard somebody say start with B. It wasn't very loud. It wasn't very confident, but it's B. All right. 1, 2, 3, 4, 5, and 6. I had to go through the longest propeller and then start going through the medium propeller, which means this would be 7, and then I got to disconnect and go up to 8. Can anybody beat 6? Following my rules. Now, my rules are IUPAC's rules. Somebody said, hey, start at A and just go over 1. Not following the rules. If I start at A, I'm going to have to do this. Number 1, number 2, number 3, number 4, number 5, number 6, and number 7. Can't beat 6. So those are the rules that you have to follow in order to number the substituents on a bicyclic system. 2 things, and then I'll shut up. What were those 2 things? Oh, here's those 2 things. That is considered a bicyclic system. But what is it missing? It's missing the third propeller. So this would be called a bicyclo 4, 1, 2, 3, 4, 2, 0 octane. Because 4 plus 2 is 6, plus the other 2 of the bridgeheads are the octane. Okay. Now, point number 2. What happens if you have more than one substituent? Give the one with that's first alphabetized. Give the one that's first alphabetized the lowest number. What if you have 2 propellers that are the same size? Do whatever you need to do to get that substituent the lowest number. The naming is an alphabetized list of substituents and numbers and the parent name. That's always the way we draw the structure. Okay. All right, pick up a graded homework set for Friday. And if you have any questions, either shoot me